In today's world, computers and electronic products are used extensively to enrich our lives.
And we could get a little flossing going in there.
Cameras, cell phones, televisions, and personal computers. All are operated by the integrated circuits found inside. These powerful silicon chips allow us to explore outer space, as well as the inner space of our own bodies. Inside these chips are complex circuit blocks. These circuit blocks contain millions of transistors and other components. They are connected by a maze of multi-layered electronic pathways. Manufacturing these massive circuits on the surface of silicon wafers requires the layering of many materials and the repetitive use of 4 major processes.
Here and there, some other very long nets that are very close to it that are cross-coupling.
Deposition, photolithography, etch, and ion implantation. In implantation, ions are accelerated to high energies and directed into the silicon substrate. This process is designed to change the electrical properties of specific regions. To see how this occurs, let's begin by looking at the molecular structure of a silicon wafer. Here we find that one silicon atom has 4 outer shell electrons that bond covalently with neighboring silicon atoms. At room temperature, the heat energy is sufficient to break a few of the silicon bonds. These free electrons, or negative carriers, conduct current, as do the empty holes, or positive carriers. Because the number of free carriers is so small, pure silicon has a high resistance to current flow. Conductivity is dramatically increased, however, when some silicon atoms are replaced with impurities called dopants. In the periodic table, dopants are close to silicon. Boron is a p-type dopant. It has only 3 electrons in its outer shell. When it is used, the missing electron behaves like a positive carrier called a hole. These holes move through the crystal, conducting current in response to applied electric fields. The crystal is called p-type. N-type materials, like arsenic and phosphorus, have 5 electrons in their outer shells. When they are used as dopants, the 5th electron acts like a negative carrier and is free to move through the lattice. This crystal is called N-type due to the extra electrons, or negatively charged free carriers. The precise control of the number and location of dopants allows engineers to carefully design silicon's electrical properties.
Take a look at what's...
We can see this at the transistor level, where the chip's wiring connects with the silicon substrate. In this simplified CMOS transistor, a deep well of doped substrate allows the coexistence of both P-channel and N-channel